In this module, we are going to learn Uzawa's two-sector model of growth. The two-sector model of economic growth given by Uzawa is basically a neoclassical model. This model states that every sector in the economy employs fixed coefficients of the factors and there is initial stage of static equilibrium in the economy. The central result of Uzawa two-sector growth model is that the uniqueness of factor market, that is the momentary equilibrium and the stability of the steady state growth path depends crucially on relative factor intensities of two sectors and attendant saving hypothesis. The most celebrated result is that we are only assured stability if the consumer goods sector is more capital intensive than the investment goods sector. In Uzawa's model, there are two productive inputs, the labor and capital, which are substitutable to each other and freely transferable from one sector to the other. Thus, Uzawa introduced a two-sector and two-factor model in the neoclassical framework.
After studying this module, you shall be able to understand the economy in a two-sector framework with two inputs. Observe the basic assumption upon which this two-sector model is based. Find out the stability conditions. To observe the changes in factor prices and commodity prices in order to fulfill the stability conditions. Examine the optimal growth path under the stable conditions and what happens if those conditions are not met. Let us begin our understanding of the model with few assumptions. This model is based upon these assumptions. Number one, there are two productive inputs, labor and capital, which can be substituted for each other. Number two, the factors are perfectly mobile across all sectors of the economy. Number three, the capital depreciates at a constant rate. Number four, the supply of labor is fixed at any point of time. The size of the labor force is exogenously determined. Number five, at any point of time, the supply of capital is determined by its existing stock. Number six, all the wages are spent on consumer goods and all the profits are reinvested. Moving on to the basic model, in a two-sector economy, two produced goods are consumer goods and the capital goods produced by using both labor and capital. Thus, this model assumes two inputs and two outputs. Moreover, one of two inputs, that is capital goods, is also an input. Thus, introduction of two sectors in the neoclassical framework raised a number of special problems for the possibility of steady growth and its stability. Next, we will discuss consumer goods sector. The production function of the consumer goods is YC, which is a function of KC and LC, where YC is output of consumer goods, LC labor used in consumer goods sector, and KC capital used in consumer goods sector. FC is the consumer goods industry production function. Now we will discuss capital goods sector. The production function of the capital goods is Yi is equal to Fi, which is function of Ki and Li. Yi is output of investment goods, Li labor used in investment goods sector, and Ki capital used in investment goods sector, while the Fi is the investment goods industry production function. Both the production functions Fc and Fi are neoclassical in the sense of exhibiting constant returns to scale, continuous technical substitution, diminishing marginal productivities to the factors, etc. Total output of two sectors is Y is equal to Yc plus P into Yi, where Y is total output of the economy, P is price of investment goods in terms of the consumer goods. Let us discuss what is the total demand for labor and capital in two sectors, where L is equal to total supply of labor. It is equal to LC plus LI, and K, which is total supply of capital, is equal to KC plus KI. Since LC plus LI are total demand for labor and KC plus KI are total demand for capital, these two equations show equilibrium in the labor and capital markets. In the labor market, the wages are just equal to the marginal product of labor and are expressed as W is equal to return to labor, that is wages. W is equal to derivative of YC with respect to LC, which is equal to Pi raised to power 1 upon 2 into derivative of Yi with respect to Li. While in capital market, the rate of return is just equal to the marginal product of capital, R, which is equal to the rate of return to capital, that is profit or interest. R is equal to derivative of Yc with respect to Kc, which is equal to Pi raised to power 1 upon 2 multiplied by derivative of Yi with respect to Ki. Further, labor supply is assumed to grow exogenously at the exponential rate n. Thus, the growth rate of labor is GL is equal to derivative of L with respect to T divided by L, which is equal to N, where N is the natural rate of growth of population. Finally, as the investment goods industry produces all the new capital goods in the economy, then ignoring depreciation, we can define the change in total stock of capital as that sector's output, that is derivative of K with respect to T is equal to Yi. So growth rate of capital is Gk, which is equal to derivative of K with respect to T divided by K, which is equal to Yi upon K. Each sector of the economy will have its own optimal capital and labor ratio, which will be Kc upon Lc for the consumer goods industry and Ki upon Li for the capital goods industry. Under the conditions of full employment, the overall capital labor ratio for the economy will be K upon L, which is equal to Kc plus Ki upon Lc plus Li, which is equal to Kc upon Lc plus Li plus Ki upon Lc plus Li, or K upon L is equal to Kc plus Ki divided by Lc plus Li, which is equal to Lc upon Lc plus Li into Kc upon Lc plus Li divided by Lc plus Li multiplied by Ki upon Li, which is equal to Lc upon Lc plus Li into Kc upon Lc plus 1 minus Li upon Lc plus Li multiplied with Ki upon Li. This shows that the capital labor ratio in the economy is the weighted average of capital labor ratio of two sectors of the economy. Uzawa further states that the allocation of labor and capital in each sector of the economy would depend upon the relative factor price ratios, that is W upon R, which further determine the ratio of prices of two commodities, that is consumer goods, and that of the capital goods, that is PC upon PI. Both industries make optimal adjustments and these yield unit cost competition that sets the price ratio PC upon PI for the two commodities equal to the ratio of unit cost. Thus, any W upon R determines an equilibrium PC upon Pi. Now let us discuss what are the conditions for stability. In the two-sector model by Uzawa, for stable equilibrium of the economy with given wage profit ratio, that is W upon R, and capital labor ratio, that is K upon L, and given the outputs YC and YI, the following conditions must be met. That is, W into L upon R into K is equal to PC into YC divided by PI into YI. This stability proposition further states that even in the growing economy, the capital labor ratio remains constant. This is possible only if growth of capital is just equal to the growth of labor force. The labor supply grows geometrically at rate lambda and is defined as delta L upon L is equal to lambda. In order to find the growth of capital stock, we must calculate delta K, which is given as under. Delta K is equal to R into K divided by Pi minus mu into K, where mu is the depreciation of capital. The stability proposition states that under conditions of equilibrium, the rate of change in capital labor ratio, that is small k is equal to K upon L, should be 0. That is, delta K upon K is equal to delta K upon K minus delta L upon L, which is equal to change in capital labor ratio in capital goods sector minus lambda minus mu is equal to 0. That is, f dash ki minus lambda minus mu is equal to 0, or f dash ki minus lambda plus mu is equal to 0. Here, the marginal product function, that is f dash ki, is a decreasing function of ki, and as ki increases, f dash k falls, and ultimately it becomes equal to lambda plus mu. Finally, another important condition of stability, which is related with above two conditions, is that the consumption goods sector is more capital intensive than the capital goods sector. Moving on to diagrammatic explanation, the factor intensity in the two sectors can be understood with help of the figure. In given figure, we have taken intensive production function of the two sectors of the economy. Here, intensive production functions are the same production functions as already defined in the basic model, but are expressed in per capita or per labor unit terms. For example, in intensive production function, these notations are used: YC is equal to YC upon L, lambda C is equal to LC upon L, small kc is equal to capital Kc upon capital LC, and Fc into Kc is equal to Fc, which is function of Kc and Lc divided by Lc. Small yi is equal to capital Yi divided by L. Lambda I is equal to capital Li upon L. Ki is equal to capital Ki upon Li. Fi Ki is equal to Fi, which is function of Ki and Li divided by Li, and small y is equal to capital Y upon L. Small k is equal to capital K upon L. In this figure, YC and YI are the production functions of the consumer goods and capital goods sectors respectively. On x-axis, on the right side, we take capital labor ratio, that is small k is equal to capital K upon L, and on the left side we have taken wage interest ratio or factor price ratio, represented as omega is equal to W upon R, while the y-axis show the per capita output of the economy as a whole, y per capita output in capital goods sector yi, and in consumer goods sector yc. Let us begin with a given capital labor ratio K star. Suppose we wish to specialize completely in the production of consumer goods, that is, suppose yi is equal to 0, so that y is equal to yc is equal to yc divided by lambda c, where lambda c is equal to 1. All labor allocated to consumer goods sector and Kc is equal to K star, so all capital allocated to consumer goods sector. We see immediately that our entire economy is governed by the intensive production function FC Kc. So with K star we produce Yc star as our aggregate output. The slope of the ray tangent to the production function is f dash c, which is equal to Rc, the marginal product of capital. The point where that ray intersects a vertical axis is equal to Wc, that is the marginal product of labor. Most importantly, the point where the tangent ray intersects the horizontal axis is omega c, which is equal to Wc upon Rc. The ratio of marginal products. If we specialize in producing consumer goods, then the ratio omega c can be seen as the resulting equilibrium factor price ratio, that is, the factor prices that clear the capital and labor markets, where the initial supply of capital and labor is captured by the given capital labor ratio, that is K star. On the other hand, if we specialize completely in investment goods production, that is Yc is equal to 0, and so Y is equal to Pi raised to power 1 upon 2 into Yi is equal to Pi 1 upon 2 into Yi divided by lambda. As lambda I is equal to 1, all labor to investment goods production, and Ki is equal to K star, all capital to investment goods. Thus, aggregate per capita output is governed by the intensive production function Fi depicted in the figure. With the given K star, notice we will produce Y is equal to Pi 1 upon 2 into Yi star, which, although this depends upon P, seems to be more than Yc star. This should alert us to the fact that the investment goods industry is less capital intensive than the consumer goods industry. Through this figure, we can also observe the relative price intensities, which are measured as the slope of ray from the origin to the relevant point on an intensive production, which is 1 upon V, the reciprocal of the capital output ratio V. Thus, letting VC and VI denote the capital output ratio in the consumer goods and investment goods industries respectively. We can see in figure 1 by the rays connecting 0 to EC and EI that 1 upon VI is greater than 1 upon VC, so that VC is greater than VI. In other words, you need more capital per unit of output in the consumer goods industry than in the investment goods industry. Relatively speaking, consumer goods are capital intensive and investment goods are labor intensive. Of course, we could have drawn this differently so that the factor intensities were reversed. We can further observe in the figure that a tangent line with slope intersects the horizontal axis at omega I is equal to Wi upon Ri, the equilibrium factor price ratio. We can easily notice that omega I is greater than omega C, which is another indication that the consumer goods industry is relatively capital intensive. Specifically, note that relative factor shares can be denoted K upon omega is equal to R into K divided by W upon L. The higher this K upon omega ratio, the greater the capital intensity. In terms of figure 1, holding K is equal to K star constant, we see that as omega I is greater than omega C, then K star upon omega I is less than K star upon omega C, indicating once again that the investment goods sector is relatively capital intensive. Thus, for a given K, the resulting equilibrium factor price ratio will depend on the allocation of two factors between the two sectors of the economy. Specifically, if all the factors are allocated to the consumer goods sector, the equilibrium will be omega C. And on the other hand, if all the factors are allocated to the investment goods sector, the equilibrium will be omega I. The assumption of strict concavity of production functions guarantees this uniqueness. If we do not know the sectoral composition of output, we cannot determine what the actual equilibrium factor price ratio omega is. It can range from a minimum of omega C, complete specialization in consumer goods, to a maximum of omega I, complete specialization of investment goods. That is, for a given K, omega minimum must be less than equal to omega, which is less than omega maximum, where omega minimum is equal to WC and omega maximum is equal to WI.
Next, we will discuss two-sector model. Similarly, we can also find a solution with given value of omega, that is the factor price ratio. This can be observed from the figure. In this figure, the given factor price ratio, that is omega star, will set a point on the horizontal axis from which emanate two rays, one with slope RC and other with slope RI, corresponding to the marginal products of capital for the consumer goods and the investment goods industries. These rays form tangencies with the intensive production functions of both the consumer goods and capital goods industries at points EC and EI respectively, which translate into resulting capital labor ratios KC and KI. Thus, this indicates the relationships between Kc omega and Ki omega, such that Kc is greater than Ki, which is another indicator of the relative factor intensity of the two sectors, and we can also notice that Kc upon omega star is greater than Ki upon omega star. We can also notice in figure that although the factor price ratio is the same for both sectors, so omega star is equal to Ri upon Wi, which is equal to Rc upon Wc. We have it that Ri is not equal to Rc and Wi is not equal to Wc. So it seems that the rates of return to capital and wages are not equal across sectors. But we must also keep in mind that price of investment goods, that is P, specifically P will be such that Pi raised to power 1 upon 2 into Ri is equal to Rc, and Pi raised to power 1 upon 2 into Wi is equal to Wc. Finally, that the amount that will be produced when factor prices are omega star can be determined from Yc divided by lambda c and Yi divided by lambda I on the vertical axis. Since both industries have positive output per capita, that is Yc and Yi, which is greater than 0, so we are not specializing exclusively in either of them. Both sectors are allowed to operate, and the particular amounts they produce will be dictated by the equilibrium factor price ratio, that is omega star. Now we will discuss factor prices and the quantities. The feasible solutions in each of the cases mentioned, that is in case of given K star and omega star, and then varying their levels can be observed from the figure. It should be noticed that varying the given K, these upper and lower boundaries for equilibrium factor prices will vary. If we observe the first figure, we can say if K is increased above K star, then both omega C and omega I will increase. We depict the resulting boundaries in figure as the upward sloping curves, that is omega C K and omega I K. We draw them as straight lines, but this is not necessarily the case. The only things that are posited are number one, that the relationship between K and omega C and omega I is unique and monotonically increasing by assumption of strict concavity and constant returns to scale for the production function. And number two, that the investment goods boundary, that is omega IK, will always lie above the consumer goods boundary, that is omega CK. From the assumption that consumer goods industry is more capital intensive than the investment goods industry. Naturally, if we change the assumption of factor intensity so that investment goods are more capital intensive than the consumer goods, then omega CK would lie everywhere above omega IK.
Moving on to factor market equilibrium locus, in figure, suppose we are given an initial aggregate capital labor ratio K0. As we say nothing about allocation between sectors, then there is a whole range of equilibrium factor prices omega which are consistent with that allocation within some maximum or minimum range. Picking one of these factor price ratio, which will then determine a sectoral allocation of Kc omega and Ki omega. But this may not be necessarily market clearing. That is, it may be that lambda C into Kc omega plus lambda I into Ki omega not equal to K0, so that our demands for factors are not equal to our initial supplies of the factor, which implies that the factor price ratio we have chosen is not appropriate. So for the initial K0, we must search for a market clearing factor price ratio that makes demand equal to supply. The line K omega in figure maps out the locus of equilibrium factor prices for every aggregate capital labor ratio. The fact that this is upward sloping everywhere and lies between the boundaries is important. Suppose we begin at K0. The locus K omega tells us that omega 0 is the market clearing factor price ratio. Thus, the corresponding sectoral allocations Kc omega 0 and K omega 0 are equilibrium allocations. That is, lambda C Kc omega 0 plus lambda I Ki omega 0 is equal to K0. In contrast, for initial capital stock K0, the wage profit ratio omega 1 is not market clearing. So, lambda C Kc omega 1 plus lambda I Ki omega 1 is not equal to K0. However, for initial capital stock K1 omega 1 is the market clearing wage profit ratio, that is lambda C Kc omega 1 plus lambda I Ki omega 1 is equal to K1. So positions A and C represent factor market equilibrium, while the positions such as B and D are factor market disequilibrium. The curve K omega is merely the locus of equilibrium positions. Thus, this model also proposes the solution if both the omega star and K star can be varied, but in each case we find that the consumption goods sector is more capital intensive than the investment sector. We have observed that for any factor price ratio, Since consumption goods sector is more capital intensive than the investment goods sector, then RKC upon WLC is greater than RKI upon WLI. Under constant returns to scale and perfect competition, it is generally the case that when the factor price ratio, that is W upon R, increases, the price ratio PC upon PI will increase or rise according to the share of wages in consumer goods sector being greater or smaller than that of the investment goods sector. Accordingly, this model states that as PC upon PI falls, W upon R rises and vice versa. Also, we can derive from the equation WL upon RK is equal to PC into YC upon PI into YI, so that K upon L is equal to W upon R multiplied with Pi Yi upon Pc Yc. An increase in W upon R raises Pi upon Pc, then K upon L must rise unless Yi upon Yc falls. But if Y upon Yc falls, there is a shift of output in favor of consumer goods, which are more capital intensive commodities, leading to a rise in overall K upon L. Thus, Ki and K must move together under the stability proposition. However, the stability condition of the consumer goods sector being more capital intensive than the investment goods sector is a sufficient condition for stability, but not necessary, as the stability may also occur even if this condition is violated. Uzawa states that in Cobb-Douglas type production function with elasticities alpha I and 1 minus alpha I for Ki and Li, and alpha C and 1 minus alpha C for Kc and Lc under full employment. The equation for demand and supply for investment goods is Rk is equal to alpha I Pi into Yi plus alpha C into Pc into Yc. But we also know that Rk is equal to Pi into Yi. Therefore, we can easily note that Pi into Yi is equal to alpha I Pi Yi plus alpha C Pc Yc. That is Pi Yi minus alpha I Pi Yi is equal to alpha C Pc Yc, or 1 minus alpha I multiplied with Pi Yi is equal to alpha C Pc Yc, or Pi Yi divided by Pc Yc is equal to alpha C divided by 1 minus alpha I. But we have also seen that Pi divided by PCYC is equal to Rk divided by WL. Therefore, Rk divided by WL is equal to alpha C divided by 1 minus alpha I. Since the elasticities in each sector of the economy are constant, the right-hand side of this equation will also be constant, showing that Rk upon WL will always remain constant. Hence, whenever R upon W falls, so Ki rises, K upon L must rise. This implies that Kc and Ki move together and stability occurs regardless of which sector is more capital intensive. However, one strong assumption regarding the stability of the system is that it occurs only if all the wages are spent on consumption and all the profits on investment goods. Robert Solow and Frank Hahn severely criticized these basic assumptions of Uzawa's model for stable growth. Solo states that it's weak an assumption for such an important result for stable equilibrium growth path. Frank Hahn went further and called the assumptions regarding capital intensity and savings as terrible assumption, which probably never or rarely hold true in the real world. It is thus reasonable to conclude from this exercise that if anything, these models have taught us that the real world is a bit more complicated than one sector model let on. Rather than the smooth convergence to a single steady state path, we find in the Uzawa two-sector model indicates that we ought to expect a good amount of indeterminacy, instability, and cyclical behavior in growth paths.
Now let us summarize what we have learned in this module. In contrast to many one-sector models, which are based on the assumption of similar production function for whole of the economy, Uzawa put forth the idea of two-sector model with different factor intensities. This immediately raises a number of special problems for the possibility of steady growth. This model is based upon two strong stability conditions. Firstly, all the wages are consumed and all the profits are reinvested. And secondly, the consumption goods sector is more capital intensive than the investment goods sector. However, this model has proposed a range of options for optimal growth path under the given factor price ratios, factor input ratios, and the commodity price ratios. It also traces the possible solutions if any of the conditions are violated.